Welcome to Lecture 2, Sets, Part 2. This is Dr. Gilbert, Eyabi. We would continue our study of sets by looking at some more properties. We start with the union of two or more sets. Union. The union of A and B is the set of elements in A or B. i.e., in mathematical notation, we say that if A and B are sets, then A union B equals the set of all elements in the universal set U, such that X is in A or X is in B. The or here is the inclusive or and not the exclusive or. How do we apply this in proofs? In proofs, we would say, let X be an element of A union B. This would mean that X is an element of A or X is an element of B. Or simply, we could just say that X in A union B implies X is in A or X is in B. We would see some examples as we move on. The intersection of A and B would be the set of elements that are common to both A and B. In mathematical notation, we say let A and B be sets. Then A intersection B is a set of all elements X in the universal set, such that X is an element of A and X is an element of B. In proofs, how do we use the concept of intersection? Let X be an element of A intersection B. Then X is in A and X is in B. Or simply, we say that X, an element of A intersection B, implies that X is an element of A and X is an element of B. Problem. Prove that A intersection B union C equals A intersection B union A intersection C. The distributivity property of intersection over union. Let's go ahead and do this proof. Let X be an element of A intersection B union C. We must show that X is an element of A intersection B union A intersection C. Okay? So we pick an element from A intersection B union C and show that X is an element of A intersection B union A intersection C. Just like we did before. But X in A intersection B union C, what does that mean? By the definition of intersection, that means X is an element of A and X is an element of B union C. Okay? What does that mean? It means X is an element of A and X is an element of B or X is an element of C. And you could put a nice parenthesis right here just so that you can read it with understanding. It means X is an element in A and, parenthesis, X is an element in B or X is an element in C. What does this actually mean? It means that X is in A and X is in B or it means that X is in A and X is in C. But what does that mean again using the definitions of intersection and union? It means X is in A intersection B, or X is in A intersection C. But that means that X is in the intersection of A and B, or, which is now union, A intersection C. And what does that mean? Let me write it very little here. That simply implies that what we started off with, A intersection B union C, is a subset of A intersection B union A intersection C. That was what is known as the forward inclusion, proving that the left-hand side is a subset of the right-hand side. We now have to prove the reverse inclusion, that the right-hand side is a subset of the left-hand side. And some of you can already guess. The empty set. The empty set is the set that has no elements, and it is denoted as that, or at times we do this, which I really don't use. Disjoint sets. These are sets that have no elements in common whatsoever, i.e., A and B are disjoint sets if A intersection B is an empty set. From time to time, you may hear the concept of mutually disjoint sets. If A1, A2, A3, AN is a family of sets, then we say that the sets are mutually disjoint if AI intersection AJ is an empty set whenever I is different from J. Both I and J are going to run from 1 to N. A family of sets A1, A2, A3 right up to AN are pairwise disjoint if AI intersection AJ is an empty set whenever I is different from J, both I and J, 1 to N. What this actually means is that if I do A1 intersection A2, I get an empty set. I do A1 intersection A10, for example, I get an empty set, and so on and so forth. The power set of a set A is simply the set of all subsets of A. This is usually denoted by P of A. From college algebra, we know that if the cardinality of A is n, i.e. A has n elements, then the cardinality of the power set of A is 2 to the n. How do we use this concept in proofs? Let X be an element of the power set of A. Then X is a subset of A. Or we simply say that X, an element of the power set of A, implies X is a subset of A. As simple as that. Problem: prove or disprove that the power set of A union B equals the power set of A union the power set of B. Now, observe that the power set is a set. So to prove that two sets are equal, what do? We prove that one is a subset of another one, and the other one is a subset of the other one. So we're going to prove the forward inclusion and the reverse inclusion, more like verifying whether both inclusions would work without cheating. So let's try that. Let's start with the forward inclusion. Let X be an element of the power set of A union B. We must verify if X is also an element of the power set of A union the power set of B. But X, an element of the power set of A union B, by definition of power set, implies that X is a subset of A union B. If X is a subset of A union B, that means that X is either a subset of A or X is a subset of B. Remember, we are using the inclusive OR. But what does this mean? By definition, it implies that X is an element of the power set of A, or X is an element of the power set of B. But by definition, that means X is an element of the power set of A union the power set of B. What does that mean? It means the power set of A union B is a subset of the power set of A union the power set of B. And that implies that our forward inclusion holds. Good job. What about the reverse inclusion? We want to check if the power set of A union the power set of B is a subset of the power set of A union B. Of course, I would leave that as a simple exercise for serious students. Once more, for students taking this class with me, I would expect you to demonstrate the reverse inclusion in class. So make sure you practice it and you know how to do it. The complement of B in A. Now, before I go ahead and define the complement of B in A, let me just say something about the complement of a set in itself. And I'm going to use an arbitrary set X. If X is a set, then we can talk of the complement of X, which is X bar, or as I prefer to write it, X prime. Okay, X is an element of X prime if and only if X is not an element of X. So what we are saying is that X prime is the set of all X in the universal set such that X is not in X. Okay, the complement of B in A is written as A minus B, and this is defined as the set of all X in the universal set such that X is in A and X is not in B. Observe that this would naturally be written as the set of all X in the universal set such that X is in A and X is in B prime, which is nothing else but A intersection B prime. In proofs, always convert A minus B to A intersection B prime. That helps. Let's look at some common sets in this class. The smallest of them is the set of positive integers z plus, then the set of integers, then the set of rational numbers, then the set of real numbers, and finally the set of complex numbers. So these are some of the sets we would be looking at in this class. Of course, we may touch a little bit on the set of irrational numbers, but our big thing would actually be with integers. Abstract algebra is all about integers. Real analysis would be all about real numbers. Complex analysis, complex numbers. The partition of a set A is the separation of a non-empty set A into mutually disjoint subsets called partite sets. Mutually disjoint subsets simply means that these subsets are pairwise disjoint. Now let's go ahead and give you an example, then define the concept more mathematically. Let A be the set defined by A, B, C, D, E, F. X1 is AD, X2 has the elements B, C, F, and X3 the element E. For the subsets X1, X2, X3 to form a partition of A, two things must happen. Number one, their union must yield A. And number two, they must be mutually disjoint. Let's check all of those. X1 union X2 union X3 would give us A, B, C, D, E, F, which is A. Also check that X1 intersection X2 is an empty set, X1 intersection X3 is an empty set, and X2 intersection X3 is an empty set. So X1, X2, X3 is a partition of A. So in general, we say that X1, X2, X3 right up to Xn is a partition of A, where A is non-empty if their union equals A, and Xi intersection Xj is an empty set whenever I is different from J, I, J1 to N, i.e. the subsets are mutually disjoint. So we're looking at something like this. And this brings us to the end of part 2 on sets. Stay tuned for section 1.2 on mappings and functions. Thank you very much.